Hello students, a very warm welcome. In this lecture, we will be beginning with inorganic chemistry, and the first topic that we will be taking up is periodic properties. In this lecture 1, we will be talking about introduction to periodic table. So we will be introducing you to the periodic table today. So let's get started. Alright, so historically, a lot many deliberations were made in order to organize the elements that were known. Alright, so first one was Lavoisier, right? First honorable mention over here is Lavoisier, and he classified the elements into two categories, right? Metals and non-metals. He said that metals, they are hard but not brittle, and non-metals, they are soft and brittle, right? Metals conduct heat and electricity, right? Non-metals generally won't conduct heat and electricity. Metals have a luster, right? They shine, right? Whereas non-metals generally have no luster. They are sonorous, right? Sonorous means that when you hit them with a hammer, right? When you hit them with something, right? What happens is they produce a sound, right? Non-metals generally didn't show such property, right? They had no sonority in general, right? So, guys, the thing was that some of the metals showed the properties of both metals and non-metals, right? As we found out later, right? So, this Lavoisier, how he categorized very simply into metals and non-metals, right? So, this was not reflective of a lot of properties that these elements showed, right? So, this was discarded, right? Then there was Taubert, right? So, what he did was he arranged similar elements in groups of three called triads, right? Groups of three elements called triads, in which the atomic mass of the central element, right, was the arithmetic mean of atomic masses of other two elements, right? Or all the three elements possessed nearly the same atomic masses, right? So it worked, right? It worked for some time. For example, lithium, sodium, potassium, right? If you see, if you add 7 and 39 and you divide by 2, it will be 23, right? Similarly over here, almost they were average, right? Or they were closer by. Okay, so, but the thing was, this triad arrangement wasn't followed by a lot many triads that he introduced over that time, right? So what he did was, for example, hydrogen, lithium and sodium was one triad. So if you add 1 and 23 and divide it by 2, you don't get 7, right? So this is very far off. Similarly this, right? And when later more elements were discovered, it was found out that less and less of these elements followed this triad property, right? This triad pattern, right? I hope you've understood this, guys. I'll move on. Then came Newland, right? What Newland did, right? He arranged it in octaves, right? Octaves means groups of 8. He arranged in groups of 8, right? So, he was the first to correlate the chemical properties of the elements with their atomic masses, right? So, this was the first major leap, right, that Newland's octave rule or Newland's octave law made in the classification of elements, right? So, according to him, if the elements are arranged in the increasing order of their atomic masses, the 8th element, right, starting from given one is similar in properties to the first one, right? So, this is what he said, right? So, this arrangement is called Newland's law of octave, right? So, octave is something similar to, right, what you have Sare Gama Padhanisa, right, in Hindi classical music. It's similar to that, right? So, it was derived basically, perhaps thought out from there, right? The idea came from there. So, it was like this. He arranged it in groups of 8 and he found out that the first element had showed similar properties to the 8th element, and he arranged this according to their atomic masses, right? But the thing was, this classification worked well in case of lighter elements, right? But there were a lot many anomalous situations when we were testing this Newland's law for heavier elements, right? It failed in case of heavier element and therefore it was discarded. right? I hope you understood. So for all this, it showed, okay, so this followed, right? But when we got to, for if you're talking about the modern periodic table, the transition elements, the inner transition element, a lot many of them, the heavier elements, didn't show the same trend, right, which Newland suggested in his law of octave. I hope you've understood this, guys. I'll move on. Then came Mendeleev, right? And Mendeleev, with absolute ingenuity, right, what he did was he arranged the elements according to their atomic masses, right? Newland did that, but again, Mendeleev took the same approach, dug deeper, right? And according to him, the physical and chemical properties, right, he got a holistic approach and he looked at it and he said that the chemical and physical properties of elements are periodic functions of their atomic masses. So they showed periodicity according to their atomic masses, right? So for example, if we are talking about atomic mass, right, so there were a lot many elements that were not known at that time, right? For example, aluminium was known, right? Aluminium was known, but he said that there would be another element, right? There would be other element which is eka aluminium, right, which comes after aluminium, right, in the same group, right? And later it was found, this gallium was found, and he was right, he predicted it, right? He said that the atomic mass of that would be 68, and it was about the same, it came out to be 70, right? Now when it came out to be 70, what the scientist who discovered this element, who found this gallium element, he went back to Mendeleev. He said that no, you said 68, but it's actually coming out to be 70. Mendeleev said that go back and check again, right? And when he got back and checked it again, he said no, you were right, Mendeleev was right, it was actually 68 point something, right? So he predicted it very, very well. Similarly for density, right, very, very close numbers, right? Melting point, he said low, and we got a low melting point, right? The formula for oxide, right, exactly the same, right? I mean, he was able to tell, right, what will be the valence shell, everything, in electrons, and how many will combine and everything, right? Formula for chloride was exactly the same. Similarly for eka silicon, right? So in the same group as silicon, the next element, the eka silicon element, was finally found, right, which was germanium, right? And you can see everything is so close, atomic masses, the density, right, the melting point, he said high, right? So this was low, 30.2, this was high, 1231, right? Then oxide, the formulas were exactly the same, the chlorides, the formula were exactly the same. So he made a major leap, Mendeleev, right? And he arranged in order of atomic masses, and this atomic mass periodicity or periodic properties according to arranging it to atomic mass, right? And this was followed for a long time, right? Before, of course, Moseley came and he tested out things, right? And he said that atomic numbers actually showed more of a correlation, of more of a linear pattern than the atomic masses, right? But Mendeleev was very, very close, and when the elements were actually discovered, it was proved that Mendeleev was right, okay? Not exactly right, but of course atomic masses were found to be less in correlation as compared to atomic numbers, but still he was right up there. All right, so, right, in fact he was able to predict that, when the elements were not discovered, right, he was able to predict, that there will be some sort of an element coming here, right? He was able to predict that, right? He was able to arrange them in 8 groups, right? So 1 2 3 4 5 6 7 8, he was able to arrange them in that, right? And things moved on from over there. Then, so this is the periodic table, right? This is the modern periodic table that we have, which is arranged according to the atomic numbers, right? So hydrogen has 1 atomic number, lithium has 3, sodium has 11, and so forth, right? So hydrogen is actually placed at 2 positions, right? 1 at 1, right? It behaves as both as a metal and a non-metal. That's a different thing, right? So there are some things that you have to remember. For example, this group, this first group, is called the alkali metal group, right? If you notice how many, so this arrangement, right, this horizontal arrangement, basically the rows, right, are called periods. So this is period 1, this is period 2, this is period 3, right, this is period 4, this is period 5, right, this is period 6, this is period 7, this is not period 8 and 9, guys, right? This fills over here, guys. There was no space over here because we wanted to arrange it in a certain pattern, more organized. We wanted to keep it, so it's just like, you know, we put in a library, right? In a library, when you have too many books of a certain category, what do you do? You compartmentalize it in some other area, right? So what you did was, actually they will be placed over here, right? They will be placed in the 6th and the 7th group respectively, but because there was no space there, so this was lifted and placed over here, and there would be more elements added over here probably, right? So these are what are known. So there are 7 periods, guys. There are 7 periods, right? And how many groups? Groups are the columns, right? So this is group 1, this is group 2, right? This is now group 3, this is group 4, group 5, 6, 7, 8, 9, 10, 11, 12, right? 13, 14, you're getting the number, 15, 16, 17, and 18. So 18 groups are there in total, right? Okay. Now, they were arranged in by their atomic numbers, right? And you might be knowing that atomic numbers are filled according to the law that in the first shell, I'm not talking about the subshell, right? The shells include the subshells, right? You must have studied that before also, right? So it's like it gets filled in the pattern 2, 8, 8, 18, 18, 32. 32, right? So 2, 8, 8, 18, 18, 32, 32, right? So this, so if we are talking about the K shell, this is K, this is L, this is M, this is N, right? This is after that, right? So K, L, M, N, and it goes like that. So it's filled in this order, right? And there is of course space left for more elements to be added in, right? I hope you've understood this, guys. So the known elements and some of the elements, right? Some of the elements that can be added which are close, right? So those can be very well organized in this periodic table, and somewhat if at a certain time, you know, which is very highly improbable, if an element with a very large atomic number comes up, right, it can be placed as an exception and its properties can be, but that will be the chances of it occurring are very low and very few of them might be found, right? So I hope you've understood. This is a very organized way of organizing the elements in the that are known to us, right? Okay, so I hope you've understood. So what we have is we have 7 periods and 18 groups, guys. All right.